Wait, there's one.
That was like marvelous.
Is that?
Maybe he doesn't take the last batch. That breaks me weird that much. There's
no quick recap.
Guess who my
Last 2 weeks. Okay.
No, it's like
So we spoke about a function called the derivative. How do we define that derivative
oh really?
for a given function? The limit definition. What is it?
Limit is h plus zero. They don't have one. F of x plus h.
Not at all.
Okay. So that, guys, the derivative, it gives you the slope of a function at a given point. It tells you about the rate of change of a function at a given point. It tells you about whether a function is increasing or decreasing, and it can help you talk about whether a function has a maximum or minimum. So we know about that. We also know about the second derivative. What does that tell us about? If I take the derivative of the derivative, give me some information I can get from that.
The slope of the tangent.
How the slope of the tangent line changes, sure. Or some other buzzwords.
The rate of change is the rate of change.
Sure. Yeah.
The concavity.
Concavity is one of the buzzwords that we care about here. In particularly, there are two kinds. What are they?
Concave up, concave down.
Concave up and down. Describe them. How would you describe concave down or concave up?
Concave up.
Up like a cup. It's talking about the shape of the graph, right? It's a smiley face. And so that can tell you that if you're increasing at an increasing rate. If you're decreasing at a decreasing rate. Concave down like a frown means you're shaping like that, so it tells you how the rate of change of the function is moving. We also looked at some properties of derivatives. So if I wanted to differentiate a constant times a function, how do I do that? It's the constant times the derivative of the function. So I can factor constants outside the derivative. What about if I wanted to differentiate a sum of functions? F of x plus or minus g of x. How do you differentiate a sum? Yeah, you differentiate each piece. And those are two properties I gave you. Some of you might be wondering why I didn't give you more. The truth is because the other ones that you would expect actually don't work. If this was a multiplication, it's not true that you can just multiply each piece, and we'll talk about that in a bit. So derivatives, you can factor constants out, you can distribute them across sums, you cannot distribute them across products or quotients, and we'll talk about that in a bit. But we do know some rules. So what is the power rule? What did that rule tell us? What kind of function did that differentiate? What did the power rule say? Yep. The derivative of
like x to the n.
X to the n is equal to
n x n minus 1.
So that was the power rule. Here notice that n is a constant. It's very important. Alright, so it's x to a number. Okay. We also spoke about the derivative of the exponential. What's the derivative of e to the x? Yeah. Yes. It's easy. I got the easy question. Okay. Slightly a little bit more technical. Not that much actually, but what is the derivative of e to some random power? I mean, there could be functions in the power, some general expression.
U prime times e to the u.
U prime times e to the u. You differentiate the power using whatever rules you might have for doing that, and then you multiply by the original function. We also use that fact to derive the derivative of ln x. What was that?
1 half x.
No.
Oh no, the 1 divided by x.
1 divided by x, that's 1 over x. So the slope of the log function is 1 over x. We also could generalize that one a little bit more. To say, if I have ln of something, how do I find its derivative? Yeah?
If we have ln something we find is denoted by putting 1 over u.
Are you done? No, that's not complete. Yeah?
The derivative of u over u.
It's the derivative of u over u. Okay? So if it's not just an x, it's some like function in there, you have to take the derivative of that function and then divide by the function itself. That's how you differentiate that back. Can you guys tell me where these two rules come from? How did we generalize these two? What did we use? How did we figure out those rules? Chain rule. Those were an application of the chain rule. So the chain rule is a function, well, it's a rule that says, this is also something that's super important to remember. Pretty much everything I just wrote on the board in this recap is super important for you to remember, and remember quickly. So what did the chain rule say?
The derivative of f of g of x.
So this talks about how to differentiate composite functions. When you have one function plugged inside another one, and you want to differentiate that new function, how did we do it? So the derivative of the outside times the derivative of the inside. And you leave the inside intact on the first one. And that's kind of where these rules came from. So here it's like your u is an inside function, so you differentiate the outside, which is itself, and then you multiply by the derivative of the inside, which is whatever you plugged into the power. Same thing with ln. If you have some function plugged in here, you differentiate the outer function, which is 1 over u, just like here it's 1 over x, but then you have to multiply by the derivative of the inside, and that gives you the u term, right? So these guys fall back on the chain rule. And in general, any basic derivative rule I give you that has just an x in it, you can actually generalize it with the chain rule to talk about when there isn't just an x. For example, you could generalize the power rule. Right? I could say, similarly, the derivative with respect to x, which means x is my variable, but what if I don't have just x? I have a whole different function, u, raised to a power. What would the derivative of that be? Well, you notice that the power is on the outside. It looks kind of like this guy. So you differentiate the outer function, which is just n times u to the n minus 1. But then because it's not just an x, you multiply by the derivative of the inside. And so that's kind of a generalized power rule. So the chain rule is very important. It talks about, you know, when things get complicated, when you don't just have an x, you can have literally anything in the place of x, and you'd still know how to differentiate it. So it's a very important rule. It's one of the fundamental rules, and it actually has an entire section devoted to itself. It's in 3.4. So we'll look at more examples of the chain rule. What I want to do now is kind of complete these properties here. We know how to deal with the derivative of a sum, but what about multiplication? How do you differentiate a product? That's what we're going to figure out now. So, again, all of these you guys should have like in your heads memorized. And I'll do a few recaps like this to make sure you guys are always reading over your notes. And of course, on a quiz, like I'm going to test you on these rules. I'll ask you, state the power rule, or state this, or state that, because it's very important that you remember these rules. That brings us to 3. And it deals with both of them. The product and the quotient. So we want to figure out how to differentiate a product. It turns out this is something that does not work. This is the wrong thing. You write it in red ink or some other colored ink if you can. right? But it turns out that if you want to differentiate one function times another, you might think you can just differentiate this one and then multiply by the derivative of that one, but that turns out to be wrong, right? So that might have been something you might have assumed before, but it's easy to see that it's wrong. You can check this. For example, we know that the derivative of x squared, what is that? It's 2x, right? We know that in two ways. We proved it from the limit definition. We also can see it from the power rule. But what if I thought of this guy as the derivative of x times x? And what if I decided to do this rule? What would have happened? Well, I would have differentiated x, which is 1, times the derivative of x is 1, which obviously is not 2x, right? So it does not work to just differentiate each part in a product and stick them together, right? So that's the main thing. So you might think, oh, it works with sums and constants can factor out, it should work with products. It turns out that it doesn't. It doesn't work there, right? So now the goal is, so how do we differentiate products? And if you ever want to figure out how to do a derivative of something that you really have no clue, you go back to the definition. This is why the definition is important. So let's actually do a definition. Let's set y equals to a product of functions f times g. Then, if I say y prime, I'm going to do the limit definition. So this is the limit as h approaches 0. I'm going to take this whole function, replace all x's with x plus h, so that would be f of x plus h, g of x plus h, minus the original function, f of x, g of x, all over h. So now my goal is to try to get a nice formula out of this for the product, the derivative of the product. So go over here and do that. Well, add a little bit so it's easy. So I'm going to do a little trick for you guys. It's kind of like I'm pulling stuff out of nowhere, but there is precedent for this. Right, you can imagine like when you're completing the square, you kind of add and subtract something that wasn't there to fit a form that you like. Or similarly, things to that, like if you want to simplify a complex fraction, you multiply by the LCD over the LCD. So you kind of introduce something that wasn't there before, but you introduce it in a very convenient way that doesn't change the answer. And that's kind of what I'm going to do here. Let's give me more space. I'm going to add and subtract something to kind of simplify this guy. And here's what I'm going to add and subtract. This f of x plus h, g of x plus h. I am going to subtract f of x, g of x. I'm going to subtract the multiplication. And add that one. Actually, don't need subtract. Plus. I don't have space. Let me start over. So from there, I'm moving here. I'm going to add and subtract that guy. Minus f of x, g of x. This is the guy that was right here. So I subtracted something and I added it back. So really I'm kind of adding 0, but I'm doing this in a convenient way. So now what I'm going to do is I want to actually split the fraction up into two parts. I can distribute a fraction across the numerators. I want to split this guy into two fractions. So my first fraction is going to be the f of x plus h, g of x plus h, minus f of x times g of x plus h, all over h. plus this one is going to be f of x, g of x plus h minus f of x, g of x, all over h. I'm going to want to simplify this fraction a bit. How can you simplify a fraction? Well, you can factor out the common term. We did this on test 1. So I'm going to say this guy is f of x plus h minus f of x, and I'll factor off the g of x plus h. Plus, here f of x is a common term, I can factor that out. And I do that for g of x plus h. And now I can go through and I can take limits. We know that the limit of a sum is the sum of the limits, the limit of products is the products of the limits, assuming these all exist. And so now when I start taking the limits, what does this guy become? What's the limit as h approaches 0 of f of x plus h minus f of x over h? That's the derivative of f. That's f prime of x. Now as h approaches 0 in this function, g of x plus h, what does that become? Literally just becomes g of x, right? Because the h goes to 0. Plus, this is f of x, times, what's the derivative of this guy? What's the limit as h approaches 0? This, again, is the definition of the derivative, so it ends up with g prime. And so this ends up being the formula for differentiating the product. That's an important formula. It's called the product rule. So let me write that down. So I have something now called the product rule. It's another very fundamental rule. Because we multiply things all the time, we need to know how to differentiate this. So it's called the product rule. And this is the rule that says the derivative of a product. So if I'm multiplying f of x times g of x. To differentiate a product, I differentiate one of the functions, multiply by the other function, plus leave the one, multiply by the other. The order in which you do this doesn't matter because you're adding two things. But that's called the product rule. Differentiate one function, leave the second, then leave the first, differentiate the second function. Add these together. That is how you differentiate a product. So for example, if you needed to differentiate x times e to the x. Right? So this is a multiplication of two functions. Now individually I know what their derivatives are, but now I'm multiplying these two. I cannot just differentiate this and differentiate that and stick them together. It's wrong to do that. So what I do is I just think of these as two different functions. This guy I can think of as my f. This guy here I can think of as my g. And then I just apply the product rule. So I'm going to do f prime times g plus f times g prime. So that's what we would know in our head. So this is f is x, so what is f prime? F prime is the derivative of f. So if this is x, what is the derivative? 1. Times g, now g is just the guy that's here, I'm just going to copy that function down. Plus f is the original function, so I'm just going to copy that down, times g prime. G prime is the derivative of g, in this case my g is e to the x, so what is g? G prime. What's the derivative of this? It's itself. So it turns out that is the derivative of x e to the x. E to the x plus x e to the x. Right? Or you could, and you don't really have to do this unless you want to set it equal to 0 or something, but you could factor out the common e to the x and that's your answer. So that's the product rule. Very important rule. We need to memorize that. Definitely for the quiz on Tuesday, I'll be asking about everything I asked you about in the recap, as well as the product rule. We'll do many more examples here. I'll just do one, but I want to prove the quotient rule for you and do another example, and then we'll do tons more examples on Tuesday. So now the question is, how do we deal with quotients? How do we deal with divisions, right? So now, if you want to differentiate something like f divided by g, these two guys are functions. What is that? Now it turns out that you can't just differentiate the top and differentiate the bottom. That still, again, won't work, right? Notice that it is not this guy. You can't just say the derivative of this is f prime over g prime. Turns out that that is actually incorrect to say that. And it's easy to do an example. Again, we know the derivative of x squared should be 2x. But let's say I rewrite x squared as something like x cubed over x. Right? That's still x squared. How do I differentiate? If I differentiated the top with the power rule, what would I get? I would get 3x squared. Differentiate the bottom with the power rule, what do I get? 1. So if I just differentiate the top and differentiate the bottom, I get this as the answer. I know that's not the answer. So this is obviously crazy to do that. So with derivatives as well, you can't, with divisions as well, you can't just differentiate each piece and stick them together, right? It works with sums, it kind of works with constants, but it doesn't work with multiplication or division. So there's like a whole rule we have to go through. But it turns out, with the chain rule and the product rule, I don't have to go to the limit definition. I can actually derive this on a slightly higher level. So we don't have to go all the way to machine language. We can use C++. I don't know if I did do computer science. Okay, so let's look at this guy. The derivative of, and it's really f of x and g of x, but I'm too lazy to write it. F over g. One thing you could do here is to rewrite f over g as f times, how can I write f over g? G to the negative 1. Now let me emphasize here that this is f of x times, there's a function here plugged inside of a power function. Which means to differentiate this part, I would need the chain rule. So let's actually use the chain rule to differentiate that, right? First of all, notice here, I just wrote it as a product, so the product rule applies. But to differentiate this piece, I will need the chain rule. So this is going to be, I'm going to differentiate the first function, leave this alone. Plus, I'm going to leave the first function alone and find the derivative of this guy. Now this guy's inside the function to the negative 1. I know how to differentiate that, that's the power rule. Bring the power down in front, leave the inside alone, subtract 1 from the power, and then I multiply by the derivative of the inside. That's the chain. And it turns out that that's how you differentiate a product. That looks slightly crazy, so let's clean this up a bit. So what I have here is, I essentially have f prime over g minus, because there's a minus sign here, I have f times g prime over g squared. Notice that that's what I have. I can rewrite this as that. I can rewrite this as that. This times this divided by that squared. So now let's create one fraction. Create the common denominator, multiply by g over g. So this gives me f prime g minus f times g prime over g squared. And it turns out that is how we differentiate a quotient. That is called the quotient rule. Quotient just means division. So this is a rule of how to differentiate divisions of functions. Do you have a question? So this rule says to differentiate something divided by something else, it's the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. This is called the quotient. And yes, personally, I literally memorize it like that in my head. I say the bottom times the derivative of the top minus the top times the bottom of the bottom squared. There are other mnemonics for this. A lot of people have like low d high minus high d low over low squared. That's something that a lot of students know about. Where the top function they call the high function, and the bottom function they call the low function. So it's the low function times the derivative of the high function, low d high, minus the high function times the derivative of the low function, high d low, and then divide by low squared. However you memorize it, you need to memorize it. Okay? So that is the quotient rule. It's a very important rule. And by the way, it's very important that you realize here that order matters. In the case of the product rule, the order did not matter. It doesn't matter which function you differentiated first, as long as you differentiated one at a time and stick them together. But in the quotient rule, the order does matter because of the negative sign. So it's possible for you to get the negative of the answer that you should be getting if you remember the order. So let's do one simple example and get out of here. Like 1 minute. X divided by e to the x. We'll discuss the product and quotient rule a little more next time. So this is, that I will think of as the f of the g. So I know my derivative is going to be equal to the bottom function times the derivative of the top minus the top function times the derivative of the bottom over the bottom function squared. That's e to the x minus x e to the x over e to the x. And of course you could simplify that. You can factor out an e to the x and cancel it. So that would just end up being 1 minus x over e to the x. In general, either of these is fine. Or we'll stop there. We'll come to an example next time using the product rule, the quotient rule, the chain rule just to get used to it. But these are the rules so far. Have them memorized and know how to do some basic examples for the next course.
Do we need to know the proof?
No, you don't need to know the proof. You just need to know the rules. Be able to actually write them down the rules. I'll ask you about them.
Do you give extra credit on proving it? Yeah, like the